Herzlich willkommen zu dieser Public Lecture Serie. Heute Morgen, wir haben 2 Public Lectures. Einmal starten wir mit Michail Makridis und dann im Anschluss nach der Pause mit Ursula Wiels. Da geht es um autonomes Fahren und Verkehr und Verkehrsmanagement. Und im zweiten Teil geht es dann um die Innovation. Ich freue mich sehr, dass ich Michail Makridis gewinnen konnte, heute diese Lecture zu halten. Er ist, wie es hier steht, der Director Traffic Engineering and Control beim IVT an der ETH, ein Stock oder 2 weiter unten. Und er ist auch Data, er hat auch früher das Institut für Data-Analyse und Prozessdesign an der Uni Zürich geleitet und setzt sich stark mit Verkehrsmanagement und zukünftigen intelligenten Verkehrssystemen auseinander. Er wird seine Vorlesung in Englisch halten, gehe ich davon aus. Und ich freue mich sehr, nachher auch, oder währenddessen seid ihr immer auch, dürft ihr auch Fragen stellen oder im Anschluss haben wir vielleicht noch Zeit für eine kleine Diskussion. Darauf freue ich mich. Jetzt übergebe ich gerne Ihnen das Wort.
Morning, everyone. Thank you, Andy, for the introduction. I will continue in English. Thank you for the invitation. My name is Michail Makridis. I'm a Deputy Director of the Traffic Engineering Group at the IVT here at ETH. And today I will talk about the disruption of autonomous driving toward future sustainable cities. And the title has some keywords and a statement. So the first keyword is autonomous driving. So the obvious question that comes is, what is this particular thing about autonomous driving that we need to bother? The second keyword is sustainable cities, and it's a bit subjective in my opinion. So what is sustainable? We have different goals. Some goals are conflicting. Maybe you want traffic efficiency, but this might introduce emissions and pollution. Maybe you increase active mobility, but this might decrease passenger traffic or goods traffic. So you have conflicting objectives. So the idea for me for future sustainable cities is first to go one step back and define how we envision them. And then there's a statement. The statement is the word disruption. So from the title of the presentation, you should expect that something big will happen, right? So in short, I can summarize my presentation in a couple of sentences now. So autonomous driving is different than human drivers. So it changes the way that traffic phenomena emerge, that disruptions happen or resolve. So it's different than human driving. This is the key, okay? The second element is data. So with autonomous driving, and especially with connected and automated vehicles, we have the opportunity to gather more data, which means better, more accurate observation of our world, which means opportunities to enrich our solutions as they exist now, and do something more efficient, something better according to our So just to give you an overview of IVT, the Institute for Transport Planning is part of the DBAU and is comprised by 3 groups, 3 main groups. It's the Transportation, Mobility and Planning Group, led by Professor Eva Heinen. It was previously the group of transport planning by Professor Hausen, who is retired. Then we have the Transport Systems Group, led by Professor Kort, who is also the director of the IVT. And then there's the Traffic Engineering Group, led by Dr. Kuvelas, who is my supervisor. So we work together there. Each group looks different things. Our group is mainly focused on the road traffic. So my presentation is divided in 2 parts. In the first part, you will not hear a lot the term autonomous driving, because the idea is to establish a common understanding, a common language of what is a road transport system, how we model, how we observe, what do we do with specific problems that we encounter, and then the second part comes to complement and say what is different with autonomous driving, right? So, what is a road transport system and why we study? The short answer is that it's a complex system that directly impacts our daily activities. So, it's something complex, meaning we cannot understand it fully, and that's why we need to somehow build knowledge around it and the phenomena that emerge. And then it impacts our daily activities. So it has direct impact on us more than once every day. So since we are all here and we don't live here, we use the road transport network to come here. So we already established a relationship with this. And it's important for us because the lecture started 7 minutes ago and we had to be present. Okay, so road transport system. In principle, it is a simple input-output thing, right? So we have a set of roads. We want to go from A to B. At the moment that we decide we use the infrastructure, we travel and we arrive in our destination. So in principle, it's very simple. The complexity comes from the fact that we are many. We want to use the system simultaneously on the same time. Now, theoretically, the capacity of our road transport system is more than enough to accommodate our needs under the requirement that we regulate our movement. So I'm living now, and maybe one of you is living in 5 minutes, and then like the airplanes, right? But there is the freedom of movement, so everyone needs to move on its own decision. So there, we use the system simultaneously, and as we will see later, we have common patterns of mobility. And this means that conflicts arise. And when conflicts arise, we need to resolve them. And each of us is a different person. Under the same circumstances, the same conditions, bilateral or multilateral conflicts are not resolved with the same way. Exactly because we are different. And there comes inefficiency. Because the conflict resolution, if it's not so efficient, it creates problems. And it creates underutilization of our infrastructure. So the potential, the nominal potential of our infrastructure cannot be reached. And furthermore, the degradation of the performance of our system is not linear. It's not that we are 3 and we degrade by alpha and we are 6 and we degrade by 2 alpha. So the degradation increases exponentially, the losses. And that's why, as traffic engineers, we need to prevent reaching some points like gridlocks where in fact we cannot do anything. That's why we apply, as we will see, traffic management and control in model systems. And the last part is that it's important to remember that we move multiple times per day, and our expectations and requirements for these movements are different. So it's a different when you have to attend a lecture, it's a different when you have to attend a business meeting, or you have to go to the hospital with your child. It's different when you want to have a beer with a friend. So furthermore, we move with different modes, cars, buses, bicycles, and so on and so forth. So just to build a bit on the socioeconomic view on road transport systems, kilometers increase over time. Fortunately, accidents decrease. So it's good, we are safer, but people want to move more and more over time. Car traffic takes the biggest share of the pie. Cars account for 72% of passenger transport, plus being more and more interconnected in terms of cities and countries, we have an increase of goods transport, which makes the problem even more challenging.
Excuse me,
Yes.
Just a quick technical question. Is this measured by passenger kilometers or by number of travels, for
Which
example?
one? You're measuring the graph here.
No, the share of
It's by passenger kilometers.
Okay. Yeah.
Even not by number of cars.
Yeah.
Yes.
Or by number of single travels, I mean.
No, by passenger kilometers.
Okay.
Okay, and then we have the energy aspect. So we have emissions, and we need to find solutions for this. And mobility is responsible for 1/3 of the energy consumption around the globe and emits 40% of the CO2. So it's a big spender, let's say. Now, if you put all these things together, you can somehow visualize now what the term sustainable future city might mean, right? Safe, being safe, have more road space for us. Actually, not road space, more space for us, green space or parks, for active mobility, for bikes and pedestrians, less cars, less pollution. Okay? And then traffic engineers started to study the problem back in 1950, and the first reaction was to create more roads. So, okay, we have congestion, let's build another lane, or let's build another road. But very soon, from 1990, we understood that this is not the solution. Actually, building more infrastructure attracts more demand. On the top of that, we don't have infinite space. So if we want to think of a lively, nice environment in the future, we cannot envision this with bridges and overlaying roads, right? So in the end, we need to find clever ways to manage our traffic and provide a good service to the users. Now, Index is a company that creates a worldwide ranking every year for different cities, and it has a set of indicators that somehow produce an estimate of the hours lost on the road every year. So in London, every year, each person loses 156 hours in congestion. And we are talking here about delays. So going from A to B, it has a nominal free flow value, a nominal travel time when the road is free, and then an additional travel time that comes from the delay, from the congestion. So if you translate this in minutes per day, here, you can see that in Zurich we lose 9 minutes per day, or 25 in London, or 23 in Paris, or 16 in Brussels. Now, the value of our time is different for each one of us, okay? If I'm a businessman and I have a high hourly charge, then this can be a huge amount of money. But maybe I'm a family guy and I want to spend these 10 or 20 minutes with my children. Or maybe I want to exercise, right? It's an important thing every day to know that you lose this amount of time, where you actually cannot do anything. And I have serious objections that with autonomous vehicles, you will be able to study in 9 minutes. Anyway, most probably you will look on your smartphone. Anyway, so how we understand, design, and study the road transport systems. Now, there are some principles for us to manage to decompose this complex system and study it. And typically, we divide it in 3 parts: in moving parts, in fixed parts, and in intangible parts. So moving parts are the vehicles and the people and the goods. Fixed parts is the infrastructure, the road. And intangible parts are the rules of the road, or the control schemes that we apply, or the traffic signals that we control and we manage. And then we have a map, and we have different types of roads, like main line or freeway. We have nodes where different roads meet in intersections, for example, or in roundabouts. And then the complexity comes with the interaction. So in this picture, you can see trucks, motorcycles, bikes, cars, pedestrians, and all these users need to somehow go to their destination and resolve the conflicts that arise. For example, here you have a speedback and the pedestrians need to do this path in order to cross the road. So, once we accept that we will not build new roads and we need to apply some clever strategy, we will work either on the demand or on the supply side. The demand is how many people want to use our network at a given time. And the supply is that I have accepted that I have a problem in my city center, so what should I do now in order to make them reach faster their destination? So the demand is one thing that we are not dealing in traffic engineering in our group. It's more of the other groups, let's say, activities, but it's important to know it. A typical thing is the M shape that we see in demand patterns, meaning that we have a peak in the morning because most of us go to their work, a peak in the afternoon because most of us return from their work, and maybe a small peak during the midday because we go for lunch for the day. This is typical for a weekday, okay? And then we have many modes already, like trams or buses or trucks, pedestrians, motorcycles. And then we have new modes like more bikes, like the presentation that you will see tomorrow with Lucas Ballo for the e-bike city. We will talk briefly about this later. And then you have delivery bicycles or scooters or autonomous and connected vehicles in the near future. What is important to remember in terms of, with regard to demand, is that we take some decisions and these decisions affect the traffic. And then the traffic affects our decisions. So it's a vicious cycle between users deciding where to go, traffic emergence, and then further decision. It's like saying that in our neighborhood there is a new mall or a new stadium that attracts people, and then we have congestion. So maybe some other people decide to go on a different path, right? The decisions, of course, can be even temporal. So you might have, for example, roadworks, right? You know that in specific roads you have roadworks, so you avoid them. Okay, let's go ahead on modeling transport. A model is a set of mathematical rules and equations that describe a physical process. So practically, we have a physical process like this presenter that if I leave it, will drop. We know how to model it. Well, actually, we find a way to model it in order to estimate the time that this object will hit the ground. Now, in this example, it's simple because we don't have wind here. The environment is somehow isolated. So we can build a model with a good accuracy, very good accuracy. In reality, regarding traffic flow, there are errors. So all the models are wrong, but all the good models have an error that is acceptable according to our specifications. Now, the models are important because in cases that we cannot use, let's say, only mathematics, like analytical descriptions, we can use them to get in physics-informed decisions. We can use them to extrapolate, generalize. We can use them for prediction or even for testing scenarios or specific strategies. And in terms of modeling in traffic engineering, we have different levels. And each level has a different aggregation, needs a different aggregation of information, has different precision, and of course, different computational complexity. So we work at microscopic level, looking at the specific vehicle or the behavior of the driver, and modeling a city traffic dynamics case study based on this principle on each individual driver. Then you have the mesoscopic, which is between like treating platoons of vehicles that are homogeneous, so you don't care how different these vehicles or the drivers are, but you assume that they are moving, let's say, together. And then you have macroscopic, where we use principles from hydrodynamic theory and fluid mechanics in order to treat traffic as liquid, as a flow. And in this case, certainly we don't care about individual vehicles and drivers. Now, there is no right or wrong. Depending on the application, if you want a real-time solution, if you want a very precise study, if you want a large study or a small study, you use different tools. Okay? And typically, macroscopic models can be used in, let's say, they are analytical, so they are more easy, let's say, for analytical investigations. While in microscopic modeling, what we do actually is the following. So we have a map of a city, and we know how a vehicle moves, and we create some models for the interaction of the vehicle with other vehicles, and we create some rules for what is a safety gap that I can do lane change. And we have different small models that we can observe with small experiments. And then we throw them into a framework, like a simulation software, and we observe. Of course, we have some data to validate that our base scenario is nice. And upon this, we build other scenarios. This is what we do at micro level. And you can see the precision here. You even consider the length of the vehicle, the spacing from the vehicle ahead, you know their speeds. You consider the lane changing, if it's mandatory because this red vehicle needs to exit the road, the ramp, or if it's discretionary because this vehicle has a slow leader. And you model also overtaking, road slope, and many other factors. Now, at macroscopic level, here you see an example from highways. You split the road in cells. So this cell can be, let's say, 200 meters long. And whatever is inside this cell, you consider it homogeneous. So what you care is three things. One thing is how many vehicles exist here. And this gives you the first fundamental quantity, that is the density. Vehicles per kilometer. Then, at this point, you measure, you just count 1, 2, 3, 4, 5 vehicles, and you take what is called traffic flow, so vehicles per hour. And then you average the speeds of the vehicles here in this space, and you have what is called space mean speed. So three fundamental quantities: speed, traffic flow, and density. I just mentioned it here more extensively because we will come back to this in a while. So here, it's even more zoomed out view where you can model Viticon as a homogeneous area or the city center as a homogeneous area. And in this case, again, you don't care about the individual vehicles or the roads or the speed limits. You assume that the operation is homogeneous. Of course, it's not. Okay? But you assume that it's homogeneous. And then you come up with tools like this that we will talk in a while that are called fundamental diagrams and give you an understanding about the traffic state in these regions, roads, or cities. So how do we observe? How do we observe? The word data comes from the Latin word datum. And datum is something given, means something given. So datum is the way for me that I see you. It may be erroneous because maybe we are in a matrix, but it's what my eyes tells me, okay? So whatever I see is something given for me, is the information, is my perception for the reality. And this is what we use in order to model, interpret, or advance our methodologies. And of course, they are necessary to take informed decision making or solve problems or understand phenomena. A fun fact is that typically the amount of data that was generated until 2000 is equal to the amount of data that we generate every day now. And as we will come back later on this, we have huge problems because not all data are the same. We have different levels of detail, aggregation, errors. We have difficulties in synchronizing them. So it's not pretty straightforward that once you have a lot of data, you will manage to propose excellent solutions. Now, the father of the fundamental diagram that collected the first, let's say, data relevant to traffic efficiency was Greensill. Around 1930s. So Greensill put this camera here and photographed sequentially the road with the cars moving here. And then he took some measurements of their speeds and how many cars they were. And he created plots like this. So here you can see the speed of the road. And here you can see the density in vehicles per mile. So the more vehicles we have on the road, the average speed decreases. Of course, when we have a couple of vehicles, then they go with the speed limit, more or less, so you have high average speed. When you have more vehicles, you start to have conflicts due to several reasons that we mentioned, like lane changing or decelerations or whatever. So then he did the regressions. He just took a couple of points, right? And he did the regression, but these graphs are still valid until today. So these guys, Wardrop and Charlesworth, in 1950s, they just took their car and they rode in London and they observed, they found a way to estimate the traffic by observing how many vehicles surpassed them during their ride. This is maybe one of the first realizations of floating vehicles. And then there is Strater, who after 20 years, he got a helicopter and he followed one vehicle and observed the traffic around this vehicle. And he got these very nice trajectories back in 1974, I think. So, how do we observe? How do we get information about what is happening? Sorry, this is for me?
Yes.
Yeah, what?
Yes, yeah, that's good.
Okay. So maybe the most common sensor that is used, and you can observe it on the road here in Zurich, there are many. It's this one. It's loop detector. So it's a wired cold thing that has a magnetic field, and then it interacts with aluminum bodies like cars, and the car distorts this field. So you know that once a car passes, you have distortion. And if you have two of them in a fixed distance, then you have another distortion after some time. So from their distance and the delay, you can also measure the speed. These are called loop detectors. Of course, we have also more modern devices like Bluetooth detectors. Each of us has a device with a Bluetooth, like a tablet or laptop or smartphone. And the Bluetooth has a unique identifier. So once we pass this first point, it identifies anonymously, of course, a device. After a while, identifies the other receiver, the same device. And from their distance again, you can measure the speed, for example, the travel time for this vehicle. Or more modern sensors like cameras that you see here, or even drones. I will show you some data later about this. There is a huge classification of sensors depending on the application. They can be point or over a segment or over a region like drones. They can be fixed or mobile sensors. They can have high frequency, reporting something every 1 second, or low frequency, reporting something every 1 minute. I'm just telling you all this because unless you know how heterogeneous is the situation here, it's difficult to understand the complexity. Lately, we managed to have some data. Google did it a couple of maybe a decade ago. So until 2009, Google collected data in collaboration with governments and agencies. After 2009, with Android, they said, okay, let's do crowdsourcing. So the user said, okay, you can track my location, and they collected the data from GPS tracks. And this is the way that Google shows us travel time estimates, which, by the way, they seem very accurate indeed for longer distances, but they're not so accurate for shorter distances. Other companies, commercial companies like here and TomTom, they use their users again and GPS devices. They track them in order to get location and speed data. Now, in terms of research, there was nothing until maybe only Triterel, that I mentioned before, until a couple of decades ago, until this NGSIM program in the US, where they put cameras in a link of 400 meters, and they extracted detailed trajectories. Now, why this is important? Because it's not only about understanding if it's congested or not a road. It's about understanding the phenomena. So you have phenomena, as I mentioned in the beginning, that they degrade exponentially the performance of the network. Like, for example, oscillations, traffic oscillations, or stop and go phenomena that I guess we all witness at some point. Okay, you're on the highway and suddenly you stop, and then you start, and then you stop. Or other more complicated phenomena that we'll not analyze here, like traffic hysteresis, for example. Now, I had the luck and opportunity to design and deploy with my colleagues in the European Commission this campaign 2 years ago, actually 4 years ago. It's called OpenACC Dataset, and practically what we did was to do experiments with platoons of vehicles that were humanly driven or autonomously driven by systems. And by setting up some scenarios, so the leading vehicle will decelerate, then will accelerate, then will decelerate again more, will accelerate faster, and so on and so forth, with specific scenarios, we observe the responses of the human drivers and the autonomous systems. Now, this project was an experimental project to serve the need of the European Commission to understand what will be the impact of automation in future networks. And the idea was to get these platoons and then extrapolate from this to roads and understand how our roads will operate with autonomous vehicles. Then there is this state-of-the-art experiment from EPFL and Professor Hieronyminis. They deployed 7 drones in the city center of Athens to observe these areas. And they synthesized the whole image, and they extracted precise trajectories for cars, taxis, bicycles over a large area. And I think it's the largest urban experiment today that gives us now the opportunity to observe the behaviors of human drivers in an urban context. And this is another state-of-the-art experiment that was finished 1.5 years ago. It's called I-24 Motion from the group of Dano work in the US. So they had these poles, camera poles, for a length of 5 miles, and they observe the road on real time. So at this moment that we are talking, they observe the road and they extract the individual trajectories on real time. And the idea, let's say the novelty of this concept, is that at any point during the day, you can deploy, for example, some bicycles or some autonomous vehicles, and you can observe how they will impact the traffic on real time. And also you avoid all this standardization that exists with experimental campaigns on safe grounds, right? Because when you go to a test track to do an experiment, you need safety constraints, the drivers know the driving cycle, so maybe there's some bias there. Well, here you have a road, you just observe it, you deploy the vehicle to do something that you want, and you observe what will happen. Now, even if we have too much data, this is not enough to get the best solution that we can get. And there are many reasons. Now, of course, there is a hype with generative models and AI. And of course, AI is an amazing tool to aggregate all this data, but we can discuss it if you want later. It's not the solution, okay? For many reasons. Typically, what we do is data fusion at the moment, and what we will continue to do. I'm pretty sure about this. So you have floating vehicles here, and you have a stationary detector. So this can be a loop detector or a camera reporting the speed over time at this specific location. And then this is a vehicle traveling on space with a specific speed, and another vehicle reporting their speeds. So you synthesize this information. Maybe your static detectors give you this, and then from the floating vehicles, you manage to get the full traffic state. So you monitor, you infer the traffic state very precisely. And this is called data fusion. So practically you combine models that have the physical information with data in order to understand what is happening. In AI, this is called physics-informed AI. So it's the same thing, okay? So they apply physical laws in order to guide and be sure that what we see is not garbage. In reality, we are here. We are on the tip of the iceberg. We don't have the capacity yet to synthesize efficiently all these data sources and exploit all the possible data that we have. Even a tweet on X now, yes, can give some information. So I'm saying Buchenplatz has an accident. This is an information. It's on a higher level. We don't know maybe when the accident happened, but someone reported it. So it's very difficult to exploit this information with the precise vehicle trajectory of a vehicle now. Yes. This was an application, an example application. So for a specific road segment, these researchers here had Bluetooth detectors. So they had this is the ground truth, how the traffic state is. And then they had loop detectors and floating vehicles. They synthesized them and they got the traffic state. So by comparing the data fused method with the ground truth, you can see that it's quite accurate. Then the important thing is the traffic management. And we're approaching autonomous vehicles. So as I said before, we don't have infinite space. We don't want to populate our space with roads. So we need to find clever ways to manage traffic. As I said before, remember, on the demand side, you convince people to move differently, or on the supply side, to resolve conflicts or degradations that happen now in our networks. So we have traffic management centers like this, that typically have screens and maybe some softwares for simulation. And they have some data from road sensors. And when they see an incident, they take some decisions. These decisions can be arbitrary, so close this lane, turn on this traffic signal, or they can be more sophisticated. It depends on the traffic management center. But it's something that happened since the 1950s. So we had humanly operated traffic signals, or change of the speed limits in Moscow by humans. Or this guy is a crazy scientist. The name is Charles Adler. I always tell the name because he was very crazy. So what he did was to create a magnetic thing here that interacted with the metal body of the car. And because there is this curve, which is not safe, it slowed down the vehicle physically. So like a magnet, it slowed down the vehicle. Of course, it didn't go into production, but it was an interesting idea. So typically, what we do in real-time traffic management is summarized in this very nice picture. On the upper part, it's the real world. On the lower part is the traffic management center. So you can see that we have our roads here and our control devices, let's say traffic signals, and we have our sensors, let's say loop detectors. The sensors give information to the traffic management center. Then there is this guy here that understands the situation, and according to the goals of this guy, he says, okay, we need to deploy a control strategy. This strategy is sent as a signal to the control devices, like the traffic signals. So this is like a summary, a very nice schematic summary of real-time traffic management. And as we said, we can manage traffic on the supply side or on the demand side. On the supply side, you change the speed limit, or you set the traffic signals to red to prevent the entrance of vehicles into a region. On the demand side, you put some price, like here in London. So you say, if you want to use the city center, if you want to enter, you need to pay. And the amount of the value that you will pay, of course, defined based on socioeconomic criteria, prevents some people from moving. In any case, management in traffic engineering, it means that a few will lose for the benefit of more. And the aim is not to go into a situation that is irreversible, like a gridlock. Now, remember Grissels that photographed the road? There are many fundamental diagrams, but all have more or less this shape. So typically, this is a graph of traffic flow. Remember vehicles per hour, how many vehicles passing a point per hour, and K, that is density, vehicles per kilometer. As K increases, more vehicles we have on the road. With more vehicles, the flow, the vehicles that pass per hour, increase. A critical point here, that is called capacity. This is the maximum number of vehicles that can be served per hour for this specific road with this fundamental diagram. The maximum. If we are able to stay here, it's perfect. Now, once more vehicles come, the flow decreases and the average speed decreases until you reach this point that is called jam density. Jam density means that everyone is stopped and you have so many vehicles in your 1 kilometer as they fit, stopped. So you cannot do anything. Practically, this value is defined by the length of the vehicle and the distance that you leave from the vehicle ahead when you stop. So control is referring mainly around this area. So we see this going down, and then we say, oh, we need to do something. We need to bring it back. This is on the supply side. Okay? So we have congestion and we do something about this. Here is a schematic representation of this graph with the congestion. It's almost free flow. Then you have excellent operation. Then you have slight congestion, and here everyone is stopped. But traffic engineers have noticed that there is this fundamental relationship of traffic flow and density also at the region level. Remember Viticon, that we consider this as a homogeneous area? So here we have Yokohama. And D'Agranzo and Geroliminis, back in 2008, empirically showed that there is this fundamental, macroscopic fundamental diagram or network fundamental diagram. That it's this one, it's similar as you can see. So as the flow increases, as the density increases the flow, you reach a nominal point, the capacity, and then the performance degrades. And how did they conclude on this nice scatter curve? Using data, loop detectors, taxi trajectories, and aggregated them. What does this mean? That we don't care if we have different taxi drivers in there. We don't care if one is aggressive or not. We take the average. And what does the average mean? That we have a variance, so we have an error. So all these traffic management strategies, of course, have an error tolerance because they aggregate situations and they assume that we are all the same, while we are not. And ultimately, we reached the second part of the presentation that is about future road transport systems. So far, we discussed what is a road transport system, why it's complex, what are the problems like safety, CO2, traffic congestion. We discussed about how we model it, how we disentangle all this complex thing into moving parts and static parts, how we observe it, what are the main sensors, what are the possibilities of getting data from Twitter or X, or from loop detectors, or from drones or cameras. But we have not discussed about autonomous vehicles. And the thing is that the future road transport system is not, let's say, a vision came directly only from autonomous driving. It's the convergence of multiple, let's say, novelties that came at the same time. We have vehicle automation, we have communication technologies that they advance very, very fast. We have electrification with Tesla and BYD and other companies like Volvo. I saw an article yesterday that Volvo increased their average sales for the first time after years due to electric vehicles. Urban planning, of course. You will hear tomorrow about the e-bike city. We have new visions. New modes of transport, like Uber Eats. And of course, the worries that we have about the climate, the fact that we have about the pollution and the problems that this creates to our health and to our children. And of course, the revolution in terms of data, right? So all these things somehow intersect and they enable a realistic, let's say, vision for our future cities. It's not about wishful thinking here. We can do it. Of course, it's not easy, but it's not about wishful thinking. The first time that I heard about autonomous vehicles was in a conference, a major conference in 2016. I was in a room. I was dealing with the OpenACC campaign there at the time. And they had a very serious discussion. What will happen if a policeman tells the car to stop and the car does not comply, and then there is a terrorist inside and start to shoot? And I was like, okay, this is science fiction. I mean, it can happen. It can be a problem that we will tackle in a decade. But talking about things that are not here, it's a bit, a bit of wishful thinking or unwishful thinking. In any case, this is not a wishful thinking. So it's a reality, it will happen. And we have the opportunity to do many things. Now, there is still a question. What about this autonomous vehicle? I mean, it's another car. If BMW gets a new model Do we revisit the way that we study our systems? No. And is this model different than the previous ones? Yes, it's very different. The modern cars are very different than the cars from the 90s. And yet we use the same models, right? With autonomous vehicles, there are a couple of things, a list of things that we will see in a while, that, let's say, call for action. First of all, just briefly to mention that depending on the capability of the autonomous vehicle, we have levels of automation, starting from level 0, a manual driver, no automation, to level 1 with systems like ABS, level 2 with systems like adaptive cruise control and lane changing autonomously, to level 3, where you can sit back and you can relax until it beeps that you take over again the control, to level 4, that you go on the highway and you can just sleep, and to level 5, that you don't need the steering wheel. So this is the way that NHTSA agency in the US somehow modeled the level of autonomy to understand what we are talking about. It's not the same thing, right? And then we have connected automated vehicles with sensors and the possibility of the vehicles to talk to each other, to the infrastructure, the traffic management center. Now, although most of the manufacturers now collect data, so their vehicles talk to the manufacturer center, so Tesla collects data. When you buy a Tesla, you sign that your data is collected, anonymously, of course, but it's collected. The same is done by Mercedes and BMW. So they have their data to improve their controllers to understand how their vehicles behave, but let's say they are not open. Actually, there are many companies that sell data. This is another problem. The open source, let's say, thing of the data aspect. But with connectivity, the vehicle has the possibility to talk. Then we have electric vehicles that have different dynamics. If you have been in an electric vehicle, they have a very high torque from 0 speed, so they can accelerate much, much faster. And acceleration, just to give you a hint, it's a very important property in terms of resolution of traffic congestion. So when you are a dynamic driver, although many drivers around might not like you, maybe you are doing good in a specific way for the traffic congestion. And this is, for me, the revolution. It's not about the autonomous vehicle. It's about the possibilities that an autonomous connected vehicle opens. It's not about me buying a vehicle and sitting there and reading my newspaper. You see that I'm old school. I said reading my newspaper. So I'm back in the paper age. Anyway, it's about new mobility concepts. It's about exploiting this information and create shared mobility or create applications that we will see in a while where the public transport is combined with autonomous vehicles or shuttles to increase the accessibility of more people in our cities. Now, we need to pay attention for these reasons. They have driver behavior that is different than humans. They don't drive the same. We will see an example. They have different vehicle dynamics, not only as an engine. Most of the autonomous vehicles will be electric, but also as a habit. When you have a controller, you need to somehow set some rules on the acceleration and deceleration strategy. It's not like a human driver that decides on ad hoc basis, based on what's happening, how much he or she will accelerate or not. It's a controller. So the dynamics are more homogeneous, are more standardized, and are different. And although this might not be obvious for you if you are not traffic engineers, I don't know, but this creates an impact on traffic. So collectively, when you have many vehicles to drive differently, you have a huge impact on the zoomed out perspective, on the macro perspective. Of course, On traffic monitoring, with data, I will show you some examples again. We can monitor traffic with floating vehicles. So if we manage to deploy some connected vehicles, even if they are not private, they are from the city, we'll have a much better understanding of the traffic. And of course, we can use them as mobile actuators. Right now, we have the traffic signals. But what if we used cars to regulate the traffic? Recently, there is a hype that I don't again understand, and I don't share the hype, but I have to tell you that some researchers in the US, they propose to add a fourth light in the traffic signal, meaning that it will be a white light, which means that all the vehicles should follow the connected vehicle. For me, it's additional complexity, but okay, we can discuss about this. So, with autonomous vehicles, you can apply traffic management and control. And then it's transport services. How you will use them? You can use them to increase the accessibility of elderly and groups that do not have access to the public transport. You can, they live in remote areas, for example. This will affect, might affect the urban planning. So, it's not a decision that is monolithic and straightforward, but the reality is that we can generate new transport services that can change the way that we move. Now, what is the expected impact? In modeling, we cannot model autonomous vehicles with the same models that we have now. I mean, it's already discussed in the literature that models that regulate the movement of the vehicle, so the longitudinal movement, the one that you see here, needs further calibration to somehow mimic the autonomous vehicle, and they have higher error. So you need new models. And of course, at a macro scale, you might need new models because you will have different traffic propagation phenomena. At a region level, you might see different macroscopic fundamental diagrams. So maybe different capacities, different degradation speed for the efficiency of the network. Then it will have an impact on road transport systems because everyone will be connected with everyone else. So the bicyclist will know when a car arrives from a black spot, or will talk with a bus, with another car, another bicycle, and so on and so forth, until we reach intelligent transport systems, where phenomenally unconnected modes, like the airplane or the ship, they will be able to synchronize with the traffic inside the city. So you can maybe in the future, you can experience a seamless service that you start from one end of the world to the other end of the world, and it's uninterrupted. Of course, this is not because of autonomous vehicles. They can be part of this, but as I said, it's because of the convergence of different technologies, data, communications, autonomous vehicles, and so on and so forth. Now, let's see each of these things. Driving behavior of AVs. This is from the OpenACC campaign that I discussed above, before, with the platoons of vehicles. And on the upper figure, on the y-axis is the speed, and on the x-axis is the time. And the black line is the leading vehicle. The yellow line is the following vehicle. In this figure, the following vehicle is an autonomous vehicle. In this figure, the following vehicle is a human driver. The driving cycles are almost identical, as you can see. However, we can see very important from traffic perspective and energy consumption perspective differences. If you observe here, the vehicle overshoots. So there was an acceleration from the leading vehicle and the follower overshooted. while the human driver did not. If you observe here, almost the black and the yellow line coincide. So the following process is very smooth. For the driver, this is not the case. Why? Because the driver does not have a set point. It doesn't say, okay, my distance from the leader is 1 second. Let's stay here. No. You intuitively decide how you will accelerate or not. So you have a variance. The autonomous vehicle has a controller. It has a point, a set point, and says, okay, I will keep a distance of 1 second. Now, this comes with the downside that when you have a disturbance, it cannot anticipate what is happening. So here, in the upper part, it couldn't anticipate this acceleration. And that's why he said, okay, let's keep 1 second, 1 second, 1 second, 1 second, and oops, he stopped. No, now let's decelerate. So this is the logic, right? It cannot see ahead. And okay, it's like, it sounds like a joke as I mentioned this, but it has a serious impact on the traffic efficiency. So one thing is this. Second thing, acceleration. Again, the variance for the autonomous vehicle is much lower than the human driver, who does not keep a steady distance. And then you can see that you have positive spikes from the human driver because humans tend to leave some space and maybe to recap and they accelerate faster. And you have some negative spikes from the autonomous vehicle because of the string instability that I mentioned before. They cannot anticipate what is happening. So at some point they need to sharply decelerate. In any case, it is interesting to note how homogeneous these spikes are for the autonomous vehicle and how heterogeneous these spikes are for the human drivers.
Can I ask a question to the previous slide?
Yes.
Isn't that speed overshoot just a question of setting the right parameters? For example, if you choose fixed distance as a parameter, then the technology should be capable of reacting in real time to this deceleration almost.
If you have fixed distance, then really your distance depends on your speed. So if you have a distance of 10 meters, right, and your speed is 10 meters per second, you have 1 second, you're 1 second away from your leader, right?
Yeah.
Now, if your speed is triple, 30 minutes, you don't have the time to react to deceleration. So you cannot keep 10 meters. Mm-hmm. I understand what you're saying, and I also do some research on finding ways to, let's say, to mitigate this impact. But in reality, manufacturers do not care. So usually, I don't want to generalize, but in many occasions, we look only our words. So a manufacturer will find a way to deploy a product that works. And then they don't care about traffic. It's a social thing. It's not a matter of performance, okay? You will not buy BMW because it helps on traffic congestion, right? So yes, they overlook this. There are some ways, but typically it's not tackled yet. Yes.
Is the flow more steady, or can you prevent that if you lower the overall speed limit? Like if it's better if you have 30 kilometers than 50?
Yes, that is a very good question. There are many concepts like this. I don't share the potential, but I have to tell you that yes, there are studies that show not about the performance, but about the safety. So they have seen that by reducing the speed limit to 30 kilometers per hour, you reduce the accidents, which is very important. Okay? In terms of traffic, typically, I mean, according to the theoretical principles, you reduce the
capacity,
the efficiency,
yeah,
and the capacity. Yes, practically, you reduce also heterogeneity. When you reduce the speed, people do not have the room to react so differently, right? When you have a speed limit of 100 kilometers per hour, you can see one going 120 and 80, you have a huge variance, even in free flow without congestion. Now, if the speed limit is 30 kilometers per hour, more or less, they will be close. So by reducing the heterogeneity, you increase the efficiency. So you have two objectives that counterbalance each other. One is that nominally you reduce the capacity. The other is that practically you increase homogeneity. So it's not proven if it works. The whole trend goes in line with the fact that we need safer roads, we need more space, we need to ban cars. So typically urban planners, they hate cars, so they want to ban them. Yes, and this is mainly my objection because I'm not a car lover, but I think that since they exist and they occupy a large share of the pie, they serve a need. So it's better to focus on the need of the people and then try to reduce the number of cars. Indeed, we need to reduce them. Tempo 30 can go towards this direction. Okay, and this is another plot again with a time headway. So here you can see that under stable following conditions, the autonomous vehicle keeps a constant time headway, time distance, while the human driver doesn't. Okay. In order to prove that, recently we had a study using AI deep learning architecture to study car following series, so trajectory observations from platoons, and decide whether it's an autonomous vehicle or a human driver. And indeed, we managed to see that we can easily distinguish autonomous driving from human driving. And of course, in terms of application, this can have numerous applications from insurance, accident, liability, monitoring in cities, management strategies in cities, and so on and so forth. But with a single camera, let's say, that you observe for 5 seconds a vehicle moving, we can understand if it's an autonomous vehicle or there's a human driver behind the wheel. Now, we talked about the driver. Let's go one step up on the monitoring, how we understand the traffic. Remember the fundamental diagram. Now, with the OpenACC, I can show you these graphs that they show the fundamental diagrams for different automation modes. This is autonomous longitudinal driving with small spacing, minimum, medium, or max spacing. This is connected and automated vehicles, and this is a human driver. And from different measurements, heterogeneous data sets, we can see, for example, that the capacity for the blue line, that is ACC, autonomous with minimum spacing, is much higher. The highest is with connectivity, is huge here. Humans are between the autonomous with long spacing and short spacing. They are here. This is the plot, speed, the second one, sorry. The second one is the speed over density. So the more vehicles we have on the road, how the speed degrades. And we can see, typically, that humans go on the green line, so ACC with maximum distance, and they tend during congestion to go to the ACC with minimum distance. So they become more aggressive and they keep smaller spaces. So why we did this? Because we understand, we want to understand the domain where we will play. So let's say this is the optimal thing, this is the suboptimal, and humans are between. And we have seen that by observing platoons, sorry?
What were the red dots again?
The red was connected and automated vehicles.
Okay.
So we have only few datasets with these, and they are experimental. So these are only preliminary findings. But typically with connectivity, they can maintain much smaller gaps with the same level of safety because they can react faster. They exchange information. And we applied in the I-24. Remember, the I-24 dataset that we said the 5-mile corridor with cameras where you can send an autonomous vehicle and see how it impacts traffic. This dataset. We managed to reconstruct the traffic flow by observing only platoons of vehicles. With 25% of autonomous vehicles, we know the traffic, we know the possible traffic states. There is no time dimension here. The fundamental diagram is the collection of all possible traffic states that you can encounter, okay? It doesn't have a time component. And here you can see that the performance changes based on the time. So from 7 to 7:15, it's a different fundamental diagram than from 7:15 to 7:30. This is not possible today to be done with existing sensors. And then we managed to reconstruct the observed that is here with our method quite accurately with only 25% of AVs. And then we are approaching to the end. And we can see another application. Here, you can see black vehicles that are human drivers and blue vehicles that are autonomous drivers. And we use them to change the speed limits and to herd the human drivers. So imagine that you have a leader that is slower than you. Maybe you can overtake, but if on the other lane you have another leader, you need to comply. So we herd human drivers, and we see great potential in terms of traffic flow and energy consumption because of what I mentioned previously about the homogenization. So they don't have, if they have a slow leader, they don't have the room, the space to variate. So you homogenize traffic and you increase the flow. Another application. Another application that is very preliminary, it's the priority pass. So we explore ways of using roads as a resource allocation problem, exploiting traffic as a resource allocation problem. So we explore the urban priority pass, where some people will buy some priority passes and will have priority in comparison to others, and the others will have the possibility on other occasions to use their priority. So we don't explore this concept as a market tool, rather than as a social tool under the motivation that today I'm in a hurry because I have to bring my child to the hospital, so I need priority. And on another day, I can give you priority and you can pass. Another application. Traffic trajectory reconstruction. So here we use these blue lines, the vehicles, without knowing the trajectories of the vehicles between here, the dotted lines. We just know when these vehicles entered and exited. And we reconstruct their trajectories in a precision level that we can reproduce. The first is the ground truth, the last is the result. We can almost reproduce the whole traffic, the full traffic, with, I think this is with 10% of connected automated vehicles. And imagine that by doing this, you can, for example, do a study about the energy consumption on the road. Knowing the precise speeds per second, you can estimate the energy consumption, the emissions, you can do many things, okay? And then we go to transport services to conclude. Of course, I think you have heard about many autonomous shuttles that are deploying. Maybe you have heard about the announcement of Elon Musk about the robotaxis. Okay. And then there are ideas at the network level to combine, as I mentioned before, autonomous vehicles with public transport and create seamless services for the users from distant, remote areas to their points of interest, maybe in the city, for example. And I will conclude my presentation with the sustainable mobility. I will leave maybe 10 minutes for questions or discussion if you want. Sustainable mobility. This is Freiburg in 1960s, a cathedral, and they had parking places in front of it. And then in 70s, they built a market. So this is one goal. Less cars, more space for active mobility, for pedestrians, or people. Here is another road, again in Freiburg, in Germany. And there are parked cars, and after some years, they build a pedestrian zone. By the way, you notice that sustainability is identical to no cars. Okay. For me, this is problematic because we need to somehow not be afraid to discuss this. But okay, anyway, this gives us an understanding on the priorities that we want for our future sustainable cities. So we want to be green, we want more space, we want less cars, obviously, and maybe cleaner air, right? And we have projects, ideas, like the Transport for London, that shows that with 20 miles per hour speed limits, the safety is improved. We have, of course, the 30 kilometers per hour that was mentioned, the Tempo 30 here in Zurich. We have concepts like the e-bike city project that says, okay, for example, you will hear more about the e-bike city tomorrow, but for me, this project was a real inspiration in a sense that really tries to reshape our mobility. Why? Because it just doesn't say just, okay, ban the cars, we don't care about them, let's build green, okay? It says, what if we change our modal habits? I mean, it can become a reality or it might not become a reality, it doesn't matter. But it's a solution that it's feasible, at least in theory. So, what if we allocate half of the infrastructure to active mobility, pedestrians and bicyclists? Of course, there is still a question, how efficient would be our life? Would it be feasible to travel at the same time from A to B? I think yes, at least in Zurich. I don't know what would happen in bigger cities, in more dense populated cities. And there are also other concepts like the 15-minute city. So let's create an island that everything we want is 15 minutes away. I hate this concept. You can see my negativity in many things. Maybe I'm exaggerating a bit just to make a point. It's not that I really hate them, but I don't think that by isolating people and confine them, let's say, in a specific area, you propose something innovative. In any case, Corbusier, for example, proposed to live in a building thousands of people. Okay, in 1940s, I don't know. Anyway, so in my view, these are pictures from Athens. On the stroller is my mother. For me, this is how we need to think sustainable future cities. We need to start from the basics. We are very fortunate that here in Zurich, most of the basics exist. But I can guarantee you that around the world, they don't exist. They are not, we should not take them for granted. And we need ramps, we need pavements, pedestrian crossings, we need driving culture. And then, once we have this, we can think of improving our road transport networks towards future and sustainable cities. Thank you very much.
Thank you very much, Michail.
So we have 10 minutes, I think.
We have 10 minutes left. Do you have any questions? Yes,
yes, thank you very much. I like your presentation and the remarks on the 15-minute city. like fast. My question is, we see that festive jam at the Gotthard, traffic jam, every once in a while. Do you have any ideas how we could manage that? Or what is the problem with the traffic at the Gotthard so that we have to stand in the Stau for hours and hours?
Yes, I don't know the specifics, to be honest, but I know, of course, about the problem. I think that it's a mixture of political decision and other things that are not, let's say, only bounded to traffic efficiency. So I know, for example, that Switzerland promotes rail transport, and not only for passengers, but also for goods. So by neglecting, let's say, one mode and favoring another, maybe it's a political decision. I don't know. For sure, it involves investing money, and the way that this money will be invested will dictate the outcome. At the moment, I don't think that Switzerland tries to find, let's say, an ultimate solution for this. I don't know the solution, but I'm pretty sure that there could be many things that can help this situation. And it's not only Gotthard, it's also the Ticino area that is suffering. For example, I know that because I was living in Italy, and I know that many Italian people live in Italy and they work in Ticino, and some Swiss people, they work in Italy. So there's this vice versa there in this region, and there are huge delays. And for me as a traffic engineer, it's a project that I would like to explore and see why it's happening, because I can see some solutions, but I guess that they are not applied for because of costs or other reasons.
I was wondering, you said at the very beginning that you're not a bit pessimistic about this AI hype.
Yes.
And for me, like thinking about autonomous driving, connectivity, I would almost logically assume that this, would help in managing the complexity and increase efficiency. So I was just wondering what your thoughts were, or where your pessimism is sourced from.
For me, AI is an excellent, amazing pattern recognizer. So the way that it works is that it is trained based on data and identifies patterns that first we cannot even identify intuitively or even statistically easy because of their complexity. There is a high order of complexity. And then yes, I forgot what was my second argument. In any case, okay. So this is a pattern identifier, a very good pattern identifier. Now, there are more things apart from this. One is that our data are not homogeneous. Our data generation is not homogeneous. So the data that you gather in Zurich might be very different than the data that you gather in London. So one is how you manage to transfer a system, an AI system for traffic prediction, for example, in our city. But the most critical thing for me at the moment is political. So in order to deploy something at social dimension, you need to be able to understand it. And by definition, deep learning architectures are not meant to be understood. They are black boxes that they give you a very good output, indeed, but you cannot understand how they concluded this output. It's not straightforward. It's a very complex nonlinear that we would need years to try to put it on paper, right? So you just rely on this. That is why we need lately to add some physical modeling inside AI, at least to know that these black boxes are bounded according to physical laws. Of course, this will degrade their efficiency eventually because you limit them, okay, to operate on a specific thing or a specific space. But in the end, they can be more trustworthy. And I think that ultimately, before deploying anything AI related, you need to first start from the physical processing. Unless you have an intuitive understanding of the situation, at least intuitive, you cannot deploy a solution for this. You cannot, for example, trust the system to manage our city, our traffic lights, without knowing how it operates. What if an optimal solution according to the AI system is, for example, to have green light in one direction for 2 hours? Okay, it's an extreme example. You can solve these issues, in fact, but I just give you this example as indicative, let's say, to say that we need to somehow tame this. Yes.
I have a question on the city scale. You proposed that the cars themselves could act as a traffic control.
Yes.
And I wonder how this works with pedestrians and bicycles, as you know, would you need the goggles, or I don't know, or maybe more in general. I guess we're going toward mixed use traffic spaces. How does this work when you have autonomous vehicles and humans that you cannot foresee what they do? Or do we need separate spaces for these?
Yes, this is a very topical question. I don't have an answer on this. I would vote for separate spaces, but at the same time, we have limitations on the space that we need to use for car traffic. This is very topical, and it's an issue, how they will operate. About the realization with the goggles, I don't know. It reminds me of the discussion in the conference about the cyber attack and the terrorist. I don't know. I don't know what the products will be, how the communication will be realized, if it will be a smartwatch or if it's goggles or if it's, I don't know. I don't know. But the idea is here. There should be somehow a framework for communication of different modes and pedestrians.
Yeah, it's a good question.
Yes.
What about this controlling all kinds of vehicles and so on? I mean, this is good for planning in different areas, but what about the data protection?
Very good question. Data protection. I'm not an expert. I know that there are many movements like AI Act or GDPR before that. It's an issue about the data protection. I don't know the solution. I don't know how it will be resolved. But it is an issue. I know that there are some ways of anonymizing them, but then we go back to the loop of the AI if we trust the encryption, if we are willing to share our data. Typically, when we decide as a community to share things, then the efficiency increases. But on the other hand, we live in a world that we don't want to share our personal lives, and it's totally understandable. And we don't have an answer on this. It's a problem that will attract a lot of attention in the next decades.
I have one question as well.
Yes.
We talked yesterday also about autonomous driving, and also that if you can own a car by your private car, the demand will increase because you can sleep within the car. So the people yesterday thought they see in 2070 or later on that it should be just public autonomous driving vehicles, not private. What's your opinion about the future? Which direction should it go? Because otherwise we have a it's a game changer now, and we can increase the capacity and so on, but in the far future, it will change.
Indeed, a major concern about autonomous vehicles is the fact that they will increase the kilometers traveled. Personally, I don't see in a free market the possibility of a solution of banning something, unless it's drugs, for example. So I don't expect that autonomous vehicles will be banned. Maybe they will be too expensive, I don't know. Yes, I see, as I said in my presentation, the potential about exploiting them in the public transport. If I had to guess, because it's just a guess, I would say that eventually we will reach a point that the car is not anymore a status of symbol or a toy for playing around, as it is right now for many people. And we will shift towards more efficient transport systems that will be based on what is called public transport, that can be also individualized transport. For example, Elon Musk lately, I don't remember when exactly, I don't think that he mentioned this explicitly, but the idea was that you own a Tesla and you leave for vacation for 3 months, and during these 3 months, you can go to the application and say that can be used as a taxi. So if we see it from this perspective, you increase a lot the utility of your vehicle, because right now our vehicles, if we own a vehicle, it stays most of the time unexploited. We use it only for 20 minutes per day, 1 hour, I don't know. But the day has 24 hours. So just as a response to additional kilometers traveled, it could be that privatized vehicles could be used for public transport, individualized public transport. I don't know. But I think that we will reach a point of maturity that we will not need anymore to have our own private car. We will have services that are good enough. As in Zurich, for example. Zurich is such an example. At least for me, coming from Greece and then from Italy, there was a huge difference in the quality of the services here. You use them intuitively because they are efficient and because you know that you will go quicker to your destination, they are comfortable. So it's a matter of service quality. In the end, we will reach that point.
Yeah, thank you very much. Thank you very much again for that interesting lecture. And we will see how we will do it within our projects as well with the design studio. So thank you very much again. Und wir machen eine Pause bis 4.